Hi, it is our pleasure to demonstrate our achievements in the field of environmental biotechnologies for rapid and efficient processing of solid and liquid hazardous organic waste. Organic waste pollution of environment is currently reaching catastrophic scale all over the world. One of the most dangerous and voluminous types is mixed food and agricultural waste. This type of waste consists of, for example, sugar beet, then potato and leaves. Each year, the disposal of such waste requires separate special measures, which are always unprofitable. Currently, biotechnologies for producing methane or hydrogen from mixed organic waste leave much to be desired. This is due to the simultaneous presence of several negative factors. First, it is the vertical design of bioreactors and too high concentration and density of solid substrates. Secondly, fermentation is inhibited by the suboptimal composition of the substrates, a mixture of silage corn and cow manure. In plant cells, the external layer of lignin, resistant to biodegradation, isolates microorganisms from contact with cellulose, and cow manure is saturated with toxic metabolites, the end products of cellulose hydrolysis in the intestines of cows. Finally, the fermentation of cellulose leads to significant acidification and accordingly to increase the inhibition of substrate fermentation and methane synthesis. To optimize the microbial decomposition of organic waste, we apply the thermodynamic prediction method. Based on this approach, we substantiated the optimal conditions for the rapid and effective decomposition of not only solid but also accompanying liquid waste. This slide presents calculation of redox potential and pH values for hydrolysis reaction of plant and animal waste under hydrogen and methane fermentation. Optimal conditions for both fermentation processes include the absence of oxygen, a low redox potential close to minus 450 millivolts, and pH close to 7.0. During the fermentation of polysaccharides from plant waste, significant acidification of the medium occurs, with pH dropping to around 4.0. Conversely, the fermentation of protein compounds leads to alkalization, with the pH rising to approximately 10. In both cases, the pH deviation by 3 units correlates with the redox potential shift of nearly 200 millivolts from the optimal value of minus 415 millivolts, which significantly inhibits fermentation and waste degradation processes. Based on the calculations, we have substantiated 3 technological operations to ensure rapid and efficient waste decomposition. The first condition involves the use of aerobic bacteria as bioreductants. Aerobic bacteria actively consume oxygen and synthesize low potential metabolites, which reduce the redox potential to minus 300 and even minus 380 millivolts, thereby creating optimal conditions for anaerobic low potential degradation of polymers. The second condition is the compensation of negative pH shift, for example acidification, through the use of inexpensive buffering agents such as soda and other similar substances. The third condition involves active mass transfer to remove toxic hydrolysis products from the surface of solid waste. This is implemented in a custom-designed modular bioreactor. The direct flow supply of wastewater into the module facilitates mass transfer and the removal of toxic end metabolites without the need for expensive or complex equipment. In the initial sections of the model, the degradation of solid waste occurs, followed by the degradation of toxic hydrolysis products in subsequent sections. To optimize and accelerate fermentation, we applied granular microbial preparation developed by us. This granular microbial preparation is intended for the degradation of a wide range of mixed solid organic waste. The distinguishing features of our preparation are as follows. Concentrated biomass of the diversified microbiome. The concentrated biomass of living cells enables fast waste fermentation, while the diversification of the microbiome allows for the degradation of a wide range of solid and liquid organic waste. Second, presence of starter substrates. These nutrient sources ensure the explosive growth of microorganisms responsible for the decomposition of organic contamination. And finally, pH and redox potential regulators. These components create optimal conditions for microbial metabolism. In light of the above, the granular preparation is highly technologically attractive. It remains its biocatalytic activity for at least 3 years. To initiate the biotechnology process, it is sufficient to simply add the dry preparation to the waste. We have discovered a module that is a direct flow installation made of transparent acrylic glass. Its length is 1.5 meters, and the dimensions of the section are 15 by 15 centimeters. Inside, there are thermal elements with adjustable temperature control. The module is equipped with a cover for its sealing. On the top cover there is a water seal consisting of 2 flasks connected in series by tubes. The first flask contains a disinfectant solution, perchlorate, and the second contained water. This water seal prevents the release of microbial aerosols and harmful gases. In the section marked with yellow, the degradation of soluble compounds, products of solid waste hydrolysis, take place due to aeration. A pump with adjustable flow rate is used to supply wastewater to the module. The wastewater is stored in these black reservoirs and, with the help of the pump, it fed into the module. The primary model substrates under investigation are 3 types of solid waste: sugar beet, potatoes, and fallen leaves. For the immobilization of microorganisms within the module, we use inert carriers in the form of nylon wire, which itself is a waste product. Microorganisms will be immobilized on these carriers. And the key accelerator of the biotechnology is a granular microbial preparation. Hydrolysis, that is the actual degradation of solid waste, is a heterophase process. This means that hydrolysis of polymers occurs only on the surface of the waste. Therefore, we investigated the efficiency of waste degradation depending on the particle size. In other words, the surface area at the same initial mass. For this purpose, we studied the fermentation efficiency of fragments with size of 2.5 centimeters, half a centimeter, and finally whole tuber vegetables. Here a linear scale of the waste particle sizes can be observed. The main goal of the research is to optimize fermentation and determine the rate of waste degradation, and later we hope simultaneous reductive detoxification of chromates. It was expected that the degradation of fragmented potato would proceed rapidly, while the degradation of whole tubers, on the contrary, would be very slow due to the small surface area of the substrate relatively to its volume. We investigated the comparative rate of degradation of whole potato tubers and those chopped into the pieces measuring 2 centimeters. The first section was loaded with 253 grams of whole potato tubers, while section 2, 3, and 4 were each loaded with 200 grams of chopped potato pieces, 2 centimeters in size. Previously, based on thermodynamic prediction, we justified that the optimal conditions for the degradation of solid waste involve obligate anaerobic hydrolysis of organic polymers under electronegative redox potential values from -200 to -300 millivolts in neutral condition at pH equal 7. Therefore, during the fermentation of waste, we monitored the redox potential and pH using potentiometric method, and additionally measured the redox potential colorimetrically using resazurin. It is well known that at a potential higher than -100 millivolts, resazurin exhibits a red color, while at potential below -100 millivolt, it becomes colorless. These graphs clearly show that during the fermentation of potatoes, that means the degradation of polymers, there is a decrease in redox potential from +200 to -130 millivolts. However, simultaneously, there is a significant acidification due to the accumulation of organic acids, such as acetate and other, which are products of carbohydrate hydrolysis. This highlights the urgent need for pH adjustment, specifically the neutralization of the culture medium. Within just 2 days of fermentation, the waste of the fragmented potato decreased 8-fold, from 200 to 25 grams. Thus, the degradation coefficient Kd was equal to 8. By the 3rd day, the fragmented potato was fully fermented, with its weight reduced by nearly 100%. This is what the remains of the fermented potato look like, just a thin, dry peel. However, the degradation of whole potato tubers, as expected, was slow. By 2nd day, the weight had decreased only from 250 to 200 grams. Nevertheless, by the 2nd day, the fermentation of whole tubers had already begun, as evidenced by their floating due to the hydrogen saturation. Similar studies were conducted to obtain patterns of fermentation of sugar beets with different fragment size. The sugar beets were introduced into the model, and the rate of their degradation, that means the reduction of their weight during fermentation, was measured. Regarding fallen leaves, a complete lack of degradation was observed. This can be explained by a high content of lignin in the leaves, a polymer that is highly resistant to microbial degradation. Therefore, it is evident that this type of solid organic waste is extremely unsuitable for both anaerobic and aerobic degradation, at least in direct flow installations. We have achieved high engineering and technological parameters in the degradation of model solid organic waste. The fermentation time was remarkably short, ranging from 3 to 5 days, and the degradation of fragmented waste with a size of 2 centimeters was exceptionally efficient. The weight of potato waste decreased by 250 times, while the weight of sugar beet waste was reduced by as much as 300 times. Spontaneous degradation of whole vegetable tubers in landfills is a very long process, taking from 1 to 2 years. However, under regulated fermentation conditions in the module, whole potato tubers were degraded in just 8 days with their weight reduced by nearly 100 times. This opens remarkable prospects for optimizing biotechnologies for waste neutralization. Evidently, the standard technological operation, waste fragmentation to accelerate fermentation, requires complex and costly equipment. However, our results demonstrate that this step can be avoided. This graph presents the integrated results of the degradation of model solid organic waste from potatoes and sugar beets. Under regulated microbial metabolism in direct flowing module, rapid and efficient waste degradation was achieved. Really, the duration of waste degradation was very short, ranging from 3 to 8 days, and the degradation coefficient Kd, representing the weight reduction multiplies, were highly significant, ranging from 96 to 530. During mixed hydrogen fermentation, anaerobic microorganisms synthesize a mixture of organic acids and alcohols, containing primarily C1, C6 carbon atoms. The concentration of this toxic compound can reach up to tens of grams per liter. Therefore, such a toxic filtrate was subsequently treated in aerobic sections. In the module, the degradation products of polymers generate abundant foam because the salts of organic acids such as acetic acid and other act as surfactants. To enhance the degradation efficiency of soluble acids and alcohols, aerobic destructors were immobilized on an inert nylon carrier. The gray color of the carrier indicates the formation of a dense microbial biofilm on it. In the aerobic sections of the module from 6 to 10, the content of soluble compounds consistently decreased. Their concentration reduced from 5,500 to 300 mg per liter, and the degradation coefficient was 18. Thus, in the continuous flow mode, rapid and efficient degradation of solid waste was achieved in the anaerobic sections from first to fourth, while soluble waste was effectively degraded in the aerobic sections from 5th to 10th. Industrial enterprises engaged in electroplating, primarily chromium plating, are significant polluters. Chromium-containing wastewater is often discharged into the environment without any treatment. All chromium-6 compounds are supertoxic metals with high redox potential and pronounced mutagenic effects. This figure shows the field stability of chromium compounds in pH redox potential coordinates. It is evident that to transform soluble chromium-6 compounds into insoluble form, it is necessary to shift the pH and redox parameters into a zone where soluble chromium-6 compounds will be reduced to insoluble chromium-3 hydroxide. The reduction of chromate can be achieved by chemical or microbiological methods. Thus, we investigated the possibility of reductive precipitation of chromates simultaneously with the anaerobic degradation of organic waste. Among the lot of reactions involving chromium compounds, only one is suitable for the reductive precipitation of chromates, namely the reduction of chromates to chromium-3 hydroxide. This reaction is highly potential with a standard redox potential plus 555 millivolts. However, during anaerobic degradation of waste, microorganisms generate a very low redox potential, close to the theoretically possible value of minus 415 millivolts. Thus, it is evident that the potential difference more than 1200 millivolts ensures maximum efficiency for the reductive precipitation of chromates by obligate anaerobes. This slide presents energy calculations based on the Gibbs equation. The free energy yield in the binary reaction of hydrogen-driven fermentation of carbohydrates and chromate reduction is very high, amounting to minus 67 kilocalories per mole. This clearly indicates the high efficiency of the reductive chromate precipitation by obligate anaerobes. The study of chromate reduction dynamics confirmed our theoretical calculations. In the upper part, high potential conditions, it means the redox potential from 400 to 500 millivolts, are formed due to the presence of chromates. However, reductants from the low potential zone with redox potential minus 280 millivolts rapidly reduce chromates in the middle zone. It is evident that injection of high potential chromate into an anaerobic environment leads to the potential spike from minus 300 up to plus 40 millivolts. However, during the chromate reduction process, the potential progressively decreased, correlating closely to its initial value of minus 290 millivolts. The reductase activity of the anaerobic microbiome is very high. Within 8 hours, the microorganism completely reduced and precipitated 3 sequentially added doses of chromate, with a total concentration of 80 milligrams of chromium-6 per liter. So we have obtained optimized engineering and technological parameters for the efficient and rapid degradation of solid and liquid organic waste. The key factors ensuring optimal process conditions include the use of granulated microbial preparation, regulation of pH and redox potential, a horizontal bioreactor design, and mass exchange facilitated by direct flow within the module, among others. The results demonstrate that the biotechnology we have developed is significantly more effective compared to current industrial biotechnologies. Specifically, the waste degradation time has been reduced by a factor of 10. The degradation efficiency coefficient was increased by a factor of 27. Additionally, filtrate has been substantially purified from liquid organic toxic waste, reducing its content by 18 times. It is important to emphasize that the filtrate from the most biogas plants, and especially from municipal landfills, is typically not treated at all. and is directly discharged into the environment. Finally, along with the degradation of solid and liquid waste, the purification of chromium-containing wastewater was also achieved. Thus, based on thermodynamic prediction, we have developed a universal environmental biotechnology that prevents pollution of the environment by solid and liquid waste as well as metals. Biotechnological research has been conducted on the basis of the Institute of Environmental Engineering and Biotechnology and on the basis of International Research and Development Center of the University of Opole. Our special thanks to Professor Agnieszka Dolchanchuk-Shryutka, Director of the Institute of Environmental Engineering and Biotechnology of the University of Opole, for scientific and organization support. We are also grateful to Professor Eva Malishevska, Head of the Department of Microbiology and Mycology of the Institute of Environmental Engineering and Biotechnology, for fruitful discussion and numerous consultation during the preparation and implementation of this project. We are also grateful for your attention and hope that our research will be of interest to both scientists and businessmen.